All right, we're live. Welcome, everyone. Welcome to another ASP.NET Community Stand-Up, where we discuss the latest updates to .NET Web development. I'm Daniel Roth, Principal Product Manager for ASP.NET Core on the .NET team. And today, I'm joined by a very special guest. We have Larry Ewing, Principal Software Engineering Manager for the Blazor team and the .NET WebAssembly runtime. Welcome,
Hey.
Larry.
Thanks. Yeah, I'm glad to be back. I'm excited to go over these things with you.
It's great to have you on the show again. Today, we're going to be talking with Larry all about performance improvements in the .NET WebAssembly runtime for .NET 10. Some pretty cool stuff. For those who don't know Larry has a long history with .NET. He's one of those very special people who has participated in some of the foundational pieces of the .NET platform and the runtime. Larry, do you want to tell us a little bit about your history with .NET and how you got started with the .NET stack?
Well, yeah, I've been doing .NET for a long time. Back in the beginning, I was working with Miguel when he started the Mono project, which was even in the early days of .NET to implement sort of .NET on Linux. And
Miguel Zacaza, right? For people who don't know Miguel, he was working on the original Mono runtime.
Yep, and throughout the years, I've been doing .NET related things kind of the whole time. Various different projects or working on the runtimes, or now for the last several years, I've been working on Blazor and the WebAssembly runtime.
Awesome. I've had the pleasure of working with Larry on .NET on WebAssembly since Blazor's, I think, very beginnings when we started exploring building a .NET runtime that could run on WebAssembly, and it's been a fantastic experience. Larry's one of those people who knows, the deep inner workings of .NET, like not just a peek under the hood, but like way down deep. He knows all the details, and so it's been a real pleasure getting a chance to work with him all these years. Before we jump into today's topic, though, we do have a few announcements that we need to go over. Let me share my screen here. First of all, it did actually happen. I think we were on the live stream last week and we were like waiting for the release. I was mashing on the refresh button. When's it going to come out? When's it going to come out? .NET 10 release candidate 1 is now publicly available, shipped just this last week. This is the first release candidate of the .NET 10 release, which means it's feature complete. And we basically think that we're done. We think that this is what we're going to ship come November at our big release party in November, the .NET Conf event. So hopefully you have your calendars marked for that. We do plan to have probably one more release candidate between now and then. Like we'll probably have another one in October based off of your feedback. Maybe a few more bug fixes, a little bit more polish. This is a go live release. So you can actually take this release. That's what it says right here. Go live release support. You can take this release and put it in production for your existing apps. Upgrade your like .NET 9 or .NET 8 apps. If you've been following the long-term support releases to .NET 10, which is the new long-term support release. Give it a try. See if you run into any problems, any issues, let us know. We're there to support you. And then we can get those things polished up for everyone by the time we ship in November. So pretty exciting. .NET 10 release candidate 1. If you haven't already downloaded it and installed it, please do today. Just click the button and get going. Also released last week was the Visual Studio 2026 Insiders Edition. This is the latest preview release of Visual Studio, new major version, moving on from 2022 by 2020. I think that wasn't a great year, right? That was still probably COVID. Let's move on to the future. 2026 is where it's at. This is the latest release of Visual Studio that comes with all sorts of really cool and great improvements for developers, AI integrated development, lots of new AI features with GitHub Copilot, much better performance, improved performance. So like build times, your developer inner loop experience is much better. I know we're doing some really great stuff with Hot Reload in Visual Studio 2026. That really, I think not all those improvements are in this first preview release, but the next one should have some really awesome stuff there to try out. And then modern look and feel. We have all the awesome new themes that have come in Visual Studio 2026. I've got it installed here. And I went through the themes. I think I went with, what was this one called? I think it was called Juicy Plum, this sort of lovely purple color. It fits with my my .NET aesthetic. If you want to try some of the other themes, you're welcome to give them give them a try. I think James Montemagno is a big fan of like bubblegum. I don't think I could do bubblegum. I'm not a bubblegum guy, Larry, but
yeah, I mean, James likes interesting colors. It's good.
Yeah, everyone's different, and that's why all the themes there are there for you. The UI design for Visual Studio now is following full fluent UI design, so it's beautiful, delightful development experience. So give that a try, and it comes in with .NET 10 RC1 included. So if you install the Visual Studio 2026 Insiders Edition, you now have .NET 10 RC1 on your box. And if you install .NET 10 RC1, you really should also install Visual Studio 2026. That's the release of Visual Studio that will be supported for .NET 10 development. So you're going to want to get it eventually. They're expected to, basically ship together come November. So you have a fully supported .NET 10 development experience with the latest, greatest tooling. Okay, so that's also available. Give it a try, install it. You can install it side by side with your existing Visual Studio 2022 install. So no worries there. Like I've got that. You can see that down here at the bottom. I've got all the Visual Studios. There's 2022 and there's 2026 side by side. This is my main dev box. No issues there. Give it a try with your existing projects and also try it with .NET 10. Okay. And some people are saying they've already been doing that and it's working nicely for them. That's great to hear. Thank you, Zenel, for sharing that. And someone is asking about, can we use the Upgrade Assistant to upgrade your existing .NET 9 and .NET 8 apps to .NET 10? Yes, you can. The GitHub Copilot app modernization tooling for .NET supports doing version-to-version .NET upgrades, like upgrading from 7 to 8, 8 to 9, 9 to 10, or 8 to 10 is supported. I know they are still working through some issues there, so your mileage may vary a little bit. I think they have I think there was even some issue with I don't remember if they were going to like have it installed with Visual Studio 2026, I think, and I think they ran into some issues with that. So there may be some gotchas with using that tooling right now, but the plan and the expectation is that by the time we get to November, people who are doing upgrades to 10, absolutely, that will be the recommended path, that you just use GitHub Copilot, point it at your projects and solutions, and it does pretty much most of the hard work for you, including handling things like breaking changes and obsolescence and those types of stuff. So yes, give that a try. All right, any other questions? Yeah, okay, great. Is there a release? Is that last tool release oriented towards humanoids instead of AI agents? I would say both. It does for both. AI and humans working together is where it's at. That's where you're going to get your maximum productivity. Okay. Other announcements. Performance improvements in .NET 10. The Tome blog post has now dropped also on the .NET blog. Steve has done this blog post now, I don't know how many years in a row, where he
quite a few. It's
enormous.
It's quite a read. It's everyone waits for it.
Yeah, it's amazingly, it's like the most popular blog post that ships on the .NET blog every single year.
I think internally and externally. I think all the .NET engineers like to read it too. So
have you made it all the way through? Like have you actually gone through a whole blog post read? There should be like a badge or an achievement unlocked for doing that. Because I think if you print it, like if you print this one, it often gets longer every year. I don't know if this one's actually officially longer than the last one, but it's like 200 pages of printed content of all the performance work that we've done for this upcoming release, across the platform. So the jets, I don't even know what half these things are because I'm not a runtime person. Like a native AOT, instruction sets, the GC, so it walks you through how you can set up the benchmarks and verify these performance improvements yourself. Just tons of performance work. The thing I love about this blog post is I think it really speaks to just the team culture on the .NET team and in the .NET ecosystem, that performance is what we do. Performance is part of us building the stack. It's not an afterthought. It's not a thing that we do every now and then. Performance is part of delivering each and every single .NET release. We want to make sure that every single time you upgrade to a new .NET 10, a .NET version, that you get that performance boost to your existing applications without you having to change even a line of code. So lots of improvements to go looking through here. Take a look and see what's here. It's pretty awesome stuff. Excellent technical work from the team. And today, what we plan to talk about is specifically some of the performance improvements that have been done for WebAssembly, for the .NET WebAssembly runtime, which is the runtime underpinnings for Blazor WebAssembly apps. When you're running your app client-side in a browser, on top of a runtime that's executing based on WebAssembly client side. Larry, this is obviously an area that you've worked on for a very long time and are familiar with the challenges with doing, building a performant .NET experience that can work in browsers. Tell us a little about what are some of the challenges that come with doing delivering an optimized .NET runtime for WebAssembly.
Yeah, typically when you talk about, especially in years past, when you talk about performance for .NET, typically what you were thinking of is JIT performance, like just-in-time compilation. Because of the restrictions of the WebAssembly virtual machine, the runtime that it runs, you can't have dynamic code, which sort of precludes doing a traditional JIT in the runtime. So you have to have alternatives. And in the case of Blazor for the WebAssembly runtime, and what we produced, the very first iteration was a simple interpreter. And at its very basic level, an interpreter is just one big loop that looks at what instructions are next, runs a little bit of machine code that relates to that instruction, and then does the next step and the next step. But it's obviously much more difficult to optimize than something like a just-in-time compiler, which can look at a full execution unit and decide how to optimize that to make sure that you preserve what should be fast. I mean, you try to get the most performance. There's also obviously ahead-of-time compilation, which we can talk about more in a bit. But basically, the fundamental challenge is that you can't do dynamic code in the WebAssembly context, at least without some other caveats that we'll also get into in a bit.
So like when we first shipped Blazor, actually the first release of Blazor was actually a server-side release. I think it was the 2019 .NET Core 3.0 release is when we shipped a Blazor server. That ran from your server execution environment, which had Core CLR, full JITted runtime, very fast, obviously, and it handled all the interactivity with the browser over the network, like by setting up a SignalR-based WebSocket connection with the browser, manipulating the DOM, and handling UI events over that channel.
Right.
I think it was about like 6 months later, like it was like a
when we did 3.2.
3.2, yeah, it was sort of an out-of-band Blazor WebAssembly we released when we got the first production-ready drop of the .NET WebAssembly runtime, and that was a interpreter-based runtime, right? Like it was just interpreting.
Yeah, it was a very simplistic .NET interpreter. It was fairly straightforward translations from IL to interpreter instructions, and ran that without a lot of optimizations.
So you're downloading normal .NET assemblies of .NET IL instructions to the browser, and then just interpreting them on the fly using a WebAssembly implementation of a .NET IL interpreter in order to get the code to execute. And obviously that has some fairly significant performance overhead in doing things that way, particularly when compared to like your server .NET runtime, which has full JIT support, or even like when you're running JavaScript, which has a native runtime that's deployed with the browser and gets the advantages of being able to execute.
Yeah, I mean, the WebAssembly runtime itself is part of the browser, and it can JIT code itself, which is what happens on the back end. But on the code we're running, we have to follow the rules, and the rules are there to enforce sort of a more secure environment. It's a sandbox to run in the browser so that you can be assured or relatively assured that whatever code you're running isn't doing anything nefarious.
Okay, so after that, like after we shipped the interpreter-based runtime, I think the next thing we did was we provided ahead of time compilation support where you could take your .NET IL instructions and ahead of time compile them down to WebAssembly.
Exactly, yeah. So ahead of time compilation, it's the basic idea. Instead of like a just-in-time compilation, you're like, well, we know what we'll probably emit here, so we'll just compile it ahead of time. And instead of including normal IL assemblies, we include machine code, or in this case, WebAssembly code. So WASM binaries that then are expected to run. The real challenge that comes in, even with the first release, which was not a very optimized version of AOT compilation for WebAssembly, there were some pretty dramatic performance improvements. One of the big challenges that comes in at that state is size. When you ahead of time compile stuff, you take something from what is often a fairly compact representation, a few instructions that are kind of high level, and you have to turn it into whatever machine is going to run that code. You have to turn it into very explicit instructions for that machine, and that typically means a much larger binary. And then in the case of Blazor and WebAssembly, you're transmitting that over the network when you're loading the page, and so size is very important both in transmission over the wire and in startup time, because you're feeding it to the browser, and that browser is going to do the JIT compilation phase, like I said, and that also takes time. So the more code that you have to do that will also impact your startup time.
The JIT of the WASM instructions.
Exactly.
Yeah.
Exactly.
So .NET IL instructions are fairly high level abstractions, whereas WASM instructions are like really low level. They're like assembly, hence WebAssembly level instructions. So you need more of those to represent the same logic that you could represent in as like a single .NET.
A few instructions of IL could be quite a bit of
WASM code.
Especially when you assume things like, oh, I need to make sure that that this can be, that exceptions can be handled and various different things that the runtime does sort of transparently. In some cases, in this case, in the WebAssembly case, those can be quite complicated and add even more code to
even more logic. Yeah. Okay. So you're trading off basically download size and basic load time performance of your application, but for better runtime performance, right? Because the ahead of time compiled WASM instructions generally is a more optimized
can be quite a bit faster, substantially faster. Yeah,
I think like in some cases like an order of magnitude, like
easily. Yeah, I mean sometimes yeah.
So much closer to what you would expect for performance of like say a JIT based .NET runtime.
Yeah, I mean you probably won't hit full parity, but you will get closer. It would it looks more like JavaScript than it does look like than an interpreter running inside a JavaScript host, which is sort of where WASM started.
And I know a lot of people might find this a little bit confusing, the idea that ahead of time compilation to WebAssembly increases the size, because I think in a lot of our like native AOT workloads where we talk about ahead of time compilation for like server workloads, we often talk about like smaller sizes and like reduced memory footprints and all the like smaller, tighter things. And that I believe is mostly because when you use native AOT on the server, you're also using the .NET IL trimmer. Like you're removing a bunch of code before you AOT it, because AOT will still make that code bigger. So you only want to AOT the stuff that you're actually going to use. So it's really
and there are complicated technical details about the native AOT has some. The IL compiler that's used for native AOT is combined with the IL linker as it goes through, so it can make decisions about how much code it has to AOT compile. Whereas the implementation that we started with in WebAssembly, it basically had to do the full static analysis using the IL linker, which we use to reduce the side, but it also has issues with sort of generic explosion where you have to emit code for every generic path, which can add quite a bit of size if it has difficulty seeing generic constraints and limiting the amount of code it has to produce. So it tends to produce more code in many cases than like native AOT would. So the size is, although native AOT can produce large binaries as well, but the big win is trimming the assemblies, and both get advantages from that. Native AOT does a better job of trimming it for AOT.
Yeah, that makes sense. Okay, so Blazor still also gets the trimming advantage before we AOT. Sounds like native AOT also has some other technical advantages that might also help it be somewhat smaller. But in general, ahead of time compiling something from the IL instructions to the native instructions will make the amount of instructions that you need more. Is the lesson there?
Yeah,
okay. At that point, you could ahead of time choose to ahead of time compile your Blazor WebAssembly app if you wanted that runtime performance boost and you were willing to trade off the download size and load time performance hit that you would take for that. And for some apps that made total sense and was totally worth it. Okay, so then what was next? Like we had the interpreter and we had AOT, and then what was it, 8 or 9? When did we ship this? The thing
I believe it was 8, where Caitlin
interpreter.
Yeah. So like I said at the beginning, JITting in WebAssembly, because you can't have dynamic code, is complicated. But you can get around some of those limitations if you operate from the JavaScript side. And what the JITterpreter, which Kate came up with, the idea is effectively you watch what the interpreter is doing, you record small traces of instructions that the interpreter is doing, gather that, and then you run it through it effectively a compilation phase. And it happens in JavaScript for the JITterpreter. That turns the interpreter opcodes into a set of WebAssembly like binary instructions into WASM directly, and then compiles that, and then uses the JavaScript APIs to link that newly compiled WebAssembly to patch imports and outputs to then start calling into that code when and basically that it's a form of JIT that your interpreter is sort of tiering into a limited JIT. And in the first iterations, it was quite limited because there are also restrictions in the browser. They've been relaxed now, but at the time that we did that work, there were strong restrictions on the size of code that you could dynamically compile in the browser to then link into the thing. So we had to do relatively small sequences of instructions that then you could compile, link, and then swap into that code. So now instead of interpreting, you're doing these traces, you're running these traces as WASM instead of an interpreter loop that's looping over them.
Sort of a hybrid interpreter JIT.
Exactly.
Like
it's not like a full JIT, but it's definitely not a traditional interpreter.
You mentioned that some of the one of the reasons why you use this approach is because of limitations about how much you can load. Was it load synchronously versus asynchronously?
Yeah.
Synchronously was one of the complaints there.
When you're feeding the WASM runtime in the browser vendors had wanted to set some limitations on how much code you could feed it to get JITted at a time. And so that sort of limited how, if you're recording what the interpreter is doing and turning that into WebAssembly, how many instructions you could really record was heavily limited by how big the WASM, how much WASM could be compiled.
It sounds like you said that some of those constraints are being relaxed. Like, is there opportunity to do more?
Yeah. As we look forward to stuff, there's options that we can explore kind of in the future. Definitely.
And we on the Blazor team, we tend to be are fairly I would say conservative in like we move to adopt new browser functionality as it becomes very broadly adopted by the people using the browsers. So we tend to not jump on new browser functionality as soon as it's available in just like one browser. We tend to kind of wait till it's broadly available.
It's a real challenge because one of the things that WebAssembly, the way it operates in browsers, is you do feature detection by the code doesn't load, which also means that sort of detecting, you would have to sculpt particular runtimes per particular feature sets if you were targeting features that weren't available in all the browsers. And our ability to do that, we do some dynamic detection and load slightly different things based on that, but doing it at the size of the entire program is too challenging for the amount of, it's much easier to target a broadly supported platform and stick with that.
You had mentioned some things about generics earlier. I'll just bring this question up to, well, that's reasonably close in the conversation. Someone was asking if we have generic support when running. I think this is asking, like, do we have generic?
I mean, we use generics all the time in the runtime. They're well supported. WASM itself doesn't even it doesn't have the concept of generics. It has, memory layouts, and it really it's a stack based. It's an odd virtual machine. It doesn't have the concept of a lot of things. It doesn't have non-local jumps. It doesn't have all sorts of stuff. So some of the challenges that we faced in the .NET runtime are actually, how do you represent these things? How do you represent some of these things that aren't supported in the runtime efficiently because they're required by .NET?
So if you're building a Blazor WebAssembly app, you can absolutely use .NET generics there. I think you were just talking earlier about some of the differences in how the native AOT toolchain deals with generics versus how the mono AOT WASM.
All our runtimes support generics. There are some interesting things about it. The thing I was trying to express is that native AOT is good. It has a better connection between the compiler and the linker, and so it can strip out some potential branches of generics that Mono can't. Mono just emits code for all of the possibilities. Or we use something called shared generic value types, which is a way to reduce that overhead, but it also gives up some performance. What it does is it emits, like, for the size of a particular argument, it emits the same code, but it means that you have to go through a marshalling function and then a demarshalling function for each of those calls. So it adds overhead to the instructions, but it reduces the size. And we try to make a reasonable set of trade-offs to hit something that's both performant and a reasonable size. But the trade-offs are different between Mono and, of course, CLR. Makes
sense. Cool. Okay. So that's kind of the history of what we have done in terms of .NET WebAssembly performance so far. So in 10, I know in Tobe's post, he has some content in here about what we've done on the WebAssembly front. Like if I go searching around in here for WebAssembly, there's this section in here, saying the mono interpreter, which is the basis of the .NET WebAssembly runtime that we use, that it gained a bunch of runtime optimizations, and it talks in here about being able to vectorize more operations. I don't know. I'm not a deep runtime person. Larry, well, can you walk us through a little bit?
Well, I can sort of. So in the process of, so I said that at the beginning, Mono started out with a very straightforward, not particularly optimized IL interpreter. As we've gone through .NET releases, part of the ways that we've gained performance is we've either added optimizations to the interpreter. There are various different ones that Vlad's implemented. He's he's sort of the major architect of the Mono interpreter. And then there are also things like vectorization, where if you're familiar with SIMD instructions on processors, it's single instruction, multiple data. You say add, but it's add 16 bytes at a time rather than 1 byte in a loop. And that's basically what vector instructions are. And as we added optimizations to the Mono interpreter and to AOT, we started implementing one of the extensions in WebAssembly is the SIMD. It's called the PAX SIMD extension. So in the base WebAssembly, this wasn't in the first version of the WebAssembly spec. It has been extended. There are multiple extensions that you can look up. One of them is the PAX SIMD extension, which is basically vector operations. And broadly speaking, it's the operations that are supported on modern processors get a single instruction in WebAssembly, with the idea that maybe you're able to call this instruction and get sort of the same benefits. And as we've been doing optimizations, we added, so for AOT, we added vectorization. So in the runtime, we call them intrinsics, which is basically like something that, it's a function in the library that actually boils down to a very specific instruction or small set of instructions at a machine level for highly optimizing cases. And the libraries team has spent several years sort of optimizing the .NET Core libraries to use vectorization on Intel and on ARM, on all the modern desktop processors. We saw an opportunity to do the same vectorization in AOT. And then after we was working in AOT, there was also some discussion, does this make sense in the interpreter context too? And, we did some testing, and Caitlin helped on this as well. And so did Radek, who's also been a big contributor to the runtime, both AOT and interpreter. Sorry, I'm getting a bunch of pop-ups on my screen for some reason. So we started first, we implemented, vector intrinsics for WebAssembly in AOT. And then as we were looking at sort of the performance guarantees, we did that. I think that first work was in .NET 8. And then in .NET 9, we looked at, hey, does this make sense to do some of these operations in the interpreter as well? And we did some basic experiments. It's kind of a funny idea, the interpreter isn't fast, but you're using these instructions. But it turns out, if you tell the interpreter to add 16 bytes at once, it doesn't have to do as much interpreting than if you say, so the same sort of pattern holds. And then in 9, we sort of figured, well, maybe we can also leverage the interpreter to turn some of these interpreter instructions into actual WebAssembly instructions using the interpreter. So then instead of sort of doing, hiding the interpreter loop from the instructions, it became, this is actually just this vector operation turns into an actual vector operation in the WASM as you're running it. And that has some really good performance benefits. And what this is talking about is that I spent some time looking at if we had gotten everything we could out of those paths. And in .NET 10, I spent some time sort of exploring where we could improve.
And we could.
If there were things still on the table, could we take advantage of it? And I found some. That's
cool. So this is taking advantage of these intrinsics, these primitives that enable optimizations, taking advantage of them in the WebAssembly runtime, like SIMD and those style of instructions. And it's kind of part of the journey, I think, that the WebAssembly standard has gone on as well. Like the original WebAssembly spec didn't have anything for SIMD, and they've had various WebAssembly extension specs that have added support for things like SIMD and so forth, that we can then take advantage of. And that, of course, takes work to actually add those optimizations. And so 10, we just added more of those cases where we're leveraging those instructions. And that has had some nice results, right? Like you were showing me this earlier, that on GitHub in the .NET Performance Repo, which is the repo I think that's used by our like performance team for a lot of.
Yeah, this is where like we run micro benchmarks on regularly every couple of days, and we record the performance of very small snippets of code, usually because they're micro benchmarks. We also have bigger performance benchmarks that run larger, but the micro benchmarks are one of those things that we keep a close eye on.
So here's the reports folder that I'm going to point people to. This is comparing .NET 9 to .NET 10. And if we go in here, and then let's just look at the README. Like down here at the bottom of this set of charts, there are a couple of charts that are specific to WebAssembly execution that are showing you, like you said, the .NET team maintains a broad array of low-level micro benchmarks, like testing very fine-grained operations in the .NET stack, and just seeing, like, as we do optimizations over the course of a release, how does this compare to the previous release? So this is not actually showing like performance improvements for a specific benchmark. This is just like counting of the benchmarks that we ran.
Yeah, of all of the thousands of benchmarks we run, how have some regressed, have some improved? What does it look like?
So green on this chart is good. Green means that it improved by some amount. And you can see down here at the bottom, like this first column is like greater than 50%, then 40 to 50%, 30 to 40%, increments of 10 basically. And so it looks like, 305 of our benchmarks have a greater than 50% performance boost. There are a few regressions down here, like 40 or so that have
actually by the release time, most of those regressions have actually been resolved.
So this data is actually like, I think it's like a month old.
Yeah, it's a month and a half old. And we took a look at this data and said, is there something we can do about those regressions? And they've, for the most part, there are still a few, but for the biggest ones have been unregressed, because it was libraries changes that caused them, and we sort of dealt with it by undoing it for mono cases, basically.
As with all things in engineering, there are trade-offs, right? Like you get all this green in exchange for just a little bit of red in some places, and even less red than that's shown in this graph, based on the newer bits. So hopefully this will be even more green by the time we get to the final GA release. And then here's the AOT chart. A little more red on this one, but I think
there's more red. AOT can be challenging to optimize for. Also, keep in mind that, quite a few of these have been resolved as well. But also, in the case of optimizing for WebAssembly, you're really optimizing for an abstract machine that then gets run in reality on a browser running on a host. So it also depends on Chrome optimizations or Edge optimizations, Safari optimizations. So sometimes things that you think will be faster don't actually turn out to be faster. And sometimes the browser makes improvements that make everything faster, or it makes regressions. One of the other things that we did during this period is we made sure that some of our WebAssembly code is now in the standard benchmarks for browsers, so that the browser vendors will at least know the directionality of some of their changes for us. They
know if they impacted us negatively, but they'll also know they also will be now optimizing for those cases.
So that's another thing worth calling out is work that the team did to make sure that we got those benchmarks.
I think they had even, it was interesting because I think it was the Edge team had actually reached out to us specifically asking for, like, hey, they would like to have some test cases that cover, .NET on WebAssembly running in a browser as part of the broader benchmark suites that they use. So even beyond the work that we do on the .NET runtime team to improve performance, the browsers, of course, do excellent work as well to optimize WebAssembly execution, making things faster.
And their knobs are actually probably bigger, but we do what we can.
Okay. So I think the big question then with these graphs is like, okay, so it looks like I see lots of green. That looks good, but how does this actually then manifest itself if I'm like building a Blazor app? And for that, what I want to point people to is again on GitHub, there's this ASP.NET Benchmarks repo, which maintains a set of benchmarks that we use for measuring ASP.NET Core performance across the stack. And of course, ASP.NET Core includes Blazor. So as part of these benchmarks, we do have Blazor WebAssembly performance benchmarks. And if you just scroll down here at the bottom, there's a benchmark report that I believe is public, so anyone can take a look at this. And if we go look at this performance benchmark report, there are a bunch of them. And the trick is once this loads, like I think the ones that you'll see here, these are like Tech Empower benchmarks. But if you click on the little numbers between the arrows down here at the bottom, you can switch to different reports. And there's one specifically for Blazor WebAssembly. And if we look at this, there's some good stuff. So like, for example, time to first UI in milliseconds is what this is showing. And if we go back to like, say, the November timeframe, where we shipped .NET 9, 243-ish, and then here back as we move forward into .NET 10, 231, so getting 5% or so in, performance improvement on time to first UI. I'm doing math in my head, so if I get the math slightly wrong, like don't get mad. In terms of like max working set, let's see, if we go look at November-ish timeframe when we shipped, looks like 967. And then more recently, we're looking at 839. So reduced working set memory usage for your Blazor WebAssembly apps. These graphs, this first graph is showing rendering performance for like rendering 1,000 items using Blazor. Huge perf drop here, performance boost. So faster is better. How long does it take to render that 1,000 items? Like quite a big improvement. 32-ish is what it looks like in milliseconds versus like 42 up above. So a good like 20% perf improvement or so. JSON serialization and deserialization performance. Hopefully you can see a slight downtrend in the
and I mean, it's important to realize that these graphs have been going down. There's a .NET 8 baseline. If you were to put, say, the .NET 5 baseline, it would be way
high.
So one of the challenges with performance work is that it's sort of diminishing returns often, where each new gain takes more work than the previous gain. Making improvements is always our goal. So even, like our goal is to end up with each release being faster than the one before, at least on net. Sometimes, as we saw in the previous thing, there are a few regressions, but the goal is to make things better.
It's fun to see the regressions pop up in these charts.
Yeah,
not here. Then
that regression is kind of interesting. That was as I was doing the vectorization work. As we talk about, like I talked about the JITterpreter and the interpreter, and the interpreter does do its own. Has its own SIMD instructions that are basically, they run SIMD code, but it's still the interpreter doing it. What happened there for those regressions that are quite substantial in the JSON thing is that I swapped instructions that were being used for vector shifts. So just the shift instruction. So it's like how many bits you shift. I don't remember if it was left or right, but it was just the shift instruction. And I dropped the JITterpreter implementation of that accidentally. So the new instruction I was using wasn't getting the JITterpreter optimization. That regression is entirely the difference between the interpreter alone and the JITterpreter optimizing that instruction. So it gives you some sense of the scale of what the JITterpreter is doing behind the scenes on top of the interpreter.
Yeah.
When you look at the deserialization, that's almost twice or more slower. It's just from not JITterpreting a shift instruction for vectors. And it's because we use the vector stuff heavily in string processing. And if it's not fast or not as fast, then it's...
So Guillaume, that's what we're just talking about, that these peaks that you see where the performance numbers jump up were check-ins that result.
That's called Larry made a mistake, and he had to figure out where he made that mistake.
Some regression at low level in the runtime, just switching like one operation for how.
It was actually particularly challenging to find that one because it was not obvious from looking at the code that would have caused that kind of regression, and so it took me a while.
But it's great to see the the engineering infrastructure doing its job, detecting these regressions so that they don't make it out to our users, and we catch them and make sure that when we ship, we're maintaining that downward trend. Down below, we also have like this is various ways of like rendering a grid. Like here's a simple like basically a quick grid like implementation. You can see that rendering. How many rows is this? I forget how many. But anyway, so some significant grid with a number of rows, like the performance of rendering that is speeding up. Same thing for just like rendering complex tables or doing simple tables. All the traditional Blazor component rendering scenarios where you just want to like display some data in HTML, those are getting faster as well.
Yeah, so they're not at the 50 to 60. improvement, but there's definitely still improvements here from that work.
So upgrade your Blazor WebAssembly apps to 10. And hopefully you should see some rendering performance boost and maybe a little bit of startup performance boost. For those with sharp eyes, you may have seen this one chart up here that doesn't look as nice. This is a published size chart about the size of the app, and we think this one is just miscounting the actual published app. We actually still need to investigate this one.
And it is
way down
I
here.
do expect some actual size regression, but I believe the bulk of that regression is from the way it's counting what's getting published, because we publish more than we actually will pull over the wire now, and that the benchmark hasn't been updated to.
Like all the fingerprinted and pre-compressed static assets, for example, as part of the published status of the app. We're probably double counting a bunch of stuff here. So we do have an infrastructure issue that we need to go there address. Like you said, it sounds like we do expect a slightly larger download size.
The trend is typically the libraries team does good work that makes things faster, but it also tends to add more
code.
Yeah.
More code to optimize, increases. And then we have to go at some point, we get tired of it and we go and say like, hey, we got
see if we can make improvements there. And one of the improvements, like right now, still Blazor is trimmed. Like we were talking about the IL trimmer earlier. One of the interesting things is Blazor is still trimmed in like the not as aggressive as it could be mode. And we'll be taking a look at if we can change some of that to do more aggressive trimming, which would also is one of the bigger deltas between, say, native AOT and what you would get with just running the trimmer as well. If you're running in partial trimming mode, it's going to be bigger than if you're running in full trimming mode. It also means some things that won't work in full trimming mode work, which is why it's enabled.
That's a great point. And by the way, we're not talking about for 10. Like 10, like we said, 10 is pretty much wrapping up.
Then it's done unless we need to make a fix.
Yes, we're making tight bug fixes, polish, taking out the diaper and polishing up the Chrome. For future releases, though, looking at getting to full trimming is something I've certainly been very interested in. For people who are curious, more details on that, when you publish your Blazor WebAssembly app today, we use the partial trimming mode, which basically means that the core framework libraries and the runtime and your app assembly will get trimmed. We'll trim those things, and then it will also trim dependencies that your Blazor WebAssembly app depends on that advertise that they support trimming, that they've been annotated to say, I can be trimmed. If you have any dependencies that don't have that annotation, then those assemblies do not get trimmed. They just get left as is. We assume that they are, that we shouldn't trim them because we might break them. But for your app assembly, I'm sorry, I should correct myself and say that you don't trim the app assembly because we assume if you put the code into your Blazor WebAssembly app, then you probably wanted it. So the app assembly itself also doesn't get trimmed. So don't put extraneous code into your Blazor WebAssembly app if you don't want it to be downloaded. So that's good to be aware of. That means that anyone out there who owns an ecosystem library for the Blazor, a library that you expect to be used in a Blazor WebAssembly app, if you haven't done the work to annotate your library to support trimming, it'd be great if you did that, because that means everyone who references your library will be able to then take advantage of trimming for that library dependency. It also means in general, for people building Blazor WebAssembly apps, keep a close eye on your dependency graph. Don't just pull in libraries willy-nilly. Like I've seen a number of cases now where people have, accidentally or just unintentionally pulled in very large dependencies that bloat the size of their Blazor WebAssembly app to 20, 30 megs of stuff that they're downloading to the browser, simply because they didn't realize that the dependency graph had grown that large. A common offender is Newtonsoft JSON. Newtonsoft JSON is a existing community JSON serialization stack. Blazor already includes a serialization stack. It includes system text JSON, which is designed for trimming and all those nice things. So you already got a JSON stack. Don't include another one. Newtonsoft JSON is a huge binary. It's like several megabytes.
And inside. It does not trim well.
It does not trim. So if you have, everyone go home, check your Blazor WebAssembly apps and see if you have a Newtonsoft JSON dependency that you don't need. See if you can get rid of it. Certainly don't pull in server dependencies into your Blazor WebAssembly apps. That will also bloat your size.
Yeah, that's what a common one is. An accidental, I need this function, and then it turns out it's pulled in 20 megabytes of
stuff size. So we will do our work on the runtime size to try and make this runtime as tight and as small as we possibly can. I think about the smallest Blazor WebAssembly app that you can ship should be roughly a meg or so, is about as small as we can get the app right now. If you do a default like Blazor WebAssembly app with all the sample code. I think that's about 2 meg, including, Bootstrap and all the, the components that includes. For if you're including a bunch of dependencies, you can quickly, make all the optimizations that we're doing not matter at all. Like a few hundred kilobytes isn't going to matter if you're pulling in Newtonsoft JSON. So check your dependency graphs for your Blazor WebAssembly apps. Okay, so that was great. Like these charts look awesome. Lots of great WebAssembly performance work has obviously been done in .NET 10. Looking forward to having these available and for full production workloads when we ship 10 this coming November.
I'm excited as well.
We've got a few questions in the chat that I think I'll bring up. I think we'll slides. Let's go to questions. Okay, so let's just go through them in order. So how does Blazor WebAssembly standalone template differ from the Blazor web app template configured with interactive WebAssembly render mode for building modern web applications? Which is better? Okay, great question. So a Blazor WebAssembly standalone app has no server component. It is just the Blazor WebAssembly part, just the client part. So you can think of it as like basically a fancy JavaScript single page app. It is a fully front-end client-side application. You can deploy it as a static site. You just need some server someplace that can serve the published files from your Blazor WebAssembly app, and that's all you need. It doesn't have any ASP.NET Core server component for it. So it's just the client-side piece. It's useful for people who want to deploy an app that they just want to be basically a static site. All the logic's going to run client-side. Okay, so that's what that template is all about. That's why it doesn't have like an app.razor file, because there's nothing to run. Well, it doesn't have. Yeah, it doesn't have a the root of the app isn't rendered using Razor from the server. It's rendered using like a static HTML file because you have no server piece to run some Razor code or C# code on the server with that template. The Blazor web app template, which is our default mainline experience for Blazor, supports is based on an ASP.NET Core server. And if you enable interactive WebAssembly rendering, then you're pairing it with the client-side piece, with the WebAssembly part. That's the part that lives in the client project. And then the server project has all the server logic. And the server project is hosting that client piece as just a bunch of basically static assets in the Blazor web app. So that's the most flexible model, because now you have .NET code on both sides of the wire. You can flexibly decide which components you want to use to run on WebAssembly and which ones you just want to render server side. It gives you the most knobs and options for deciding how your app gets rendered. So that's the difference between those two. Hopefully that helps. All right, so the next one. Any improvements in tooling for Razor in the new Visual Studio 2026 Insiders Edition? The answer is yes. I alluded a little bit to some of the hot reload work that we've been doing for Visual Studio 2026. Most of those improvements are not turned on by default yet in the current Insiders release. But if you go into, maybe I can show this. If you go into Visual Studio, and this is, I think we posted on some social media, popular .NET social media locations that you can do this. If you go in here and you look for, let's see, how do I find it? Co-hosting. Blazor hosting, is it? Somewhere in here. This one. I think it's this one. Let me see if I can bring it up. Yeah, so oh my goodness, I'm having trouble like searching through all these. So use Roslyn, this one. Yeah. Use Roslyn co-host server for Razor. Okay, you can see that right now it's off by default. And if you just installed Insiders Edition, it will be off for you. We haven't turned it on yet. We plan to turn it on in the next update of Visual Studio 2026, the next preview update. But if you want to, you can go ahead and check that checkbox. And what that does is it takes the Razor language server and the C# Roslyn language server, and it co-hosts them together. It co-hosts the Razor stuff with Roslyn, which improves performance tremendously and also simplifies the architecture of the tooling. So that will change both the editor experience and also dramatically speed up a hot reload when you're hot reloading things from Razor. So if you want to give that a try today, you can go ahead and check that checkbox and give it a shot. If you run into any things in the tooling or hot reload that you're not happy with, click the Visual Studio send feedback button, this guy up here in the corner, that send feedback button, click that and open a Visual Studio feedback ticket to let us know if you're hitting any problems there. But co-hosting is a big one that should make hot reload much faster and make the Razor tooling much simpler and more reliable, and it will be the foundation that we can then use to make future Razor tooling investments. All right. I just showed a whole bunch of that, and you guys couldn't see any of that, could you? Because I didn't share my screen. I was like, what are you showing, Dan? Oh, that's hilarious. Okay, let me do this again. There's the new setting. Use Roslyn co-host server for Razor. That's what you want to check. Okay, Larry, you were just sitting there like, nodding. Like,
you were talking. I thought I'd let you go with it.
Okay, that's the option that will cause the 2 language servers to be co-hosted. It will speed up hot reload and also make the Razor editor use the new experience, which should be much more reliable. And if you run into issues, up here above, right there, that's the send feedback button that you can use for sending any Visual Studio feedback problems. All right. Sorry about that, folks. Okay. Next question. On WASM, the transition of static to interactive is much slower than compared to Blazor server. Is there a way to improve that? So I think this is talking about pre-rendering, right? So when you have a component in Blazor that's using one of the interactive render modes, like using like Blazor server or using Blazor WebAssembly, which means you can handle UI events and dynamically react to what the user is doing. By default, we will pre-render that component statically from the server, so we can just get some HTML down to the browser as fast as we can while we set up the interactivity. Setting up the interactivity might mean setting up the WebSocket connection with the server, or it might mean downloading the WebAssembly runtime and getting that booted up and getting the components running on top of that runtime. So there's a bit of a delay between when you get that initial static rendering, the pre-rendering, and when you actually have full interactivity. With Blazor server, there's just less work to do. Like, all you have to do is set up the WebSocket connection. You're off and running, right? With Blazor WebAssembly, you have to download the runtime and get it started, so which takes longer. So that's why there's a difference in delay from when you see the first HTML show up and then when the component is actually fully interactive. Ways to improve that. Well, with WebAssembly, that means we need to make the runtime startup faster. So you saw some of the first UI improvements that we have in 10. And we've been talking about other things that we can do to improve that. Making the runtime and the app smaller, of course, helps because there's less stuff to then download. That's work that we can do on our side to speed things up. On your side, make sure your dependency graph is not gone crazy on you. Any other thoughts on that one, Larry?
No, I mean, we are always looking at ways to improve startup, and we did do some work in 10 that should help both with caching and startup performance. Hopefully, it depends. Like, some startup things scale with the size of your app, so if your app is relatively small, it doesn't matter nearly as much as when your app is bigger. So it's worth trying to see if you get improvements. But yeah, it's a challenge to get everything across and start it up, and we will continue to see if we can make improvements.
Cool. All right. Question about GC in WebAssembly. So one of those extension specs. So how is the GC solved in the WebAssembly version? Is there a built-in GC, or does .NET have to roll their own?
So yeah, this is an interesting question that comes up pretty often. There is a WebAssembly extension, like one of the specs that has been fully ratified. So that is GC for WebAssembly. The issue there is that it's not really usable from .NET because of some of the design choices that .NET has made over the years that make it, we need access to the low-level objects to do some of the optimizations we do. Basically, we assume that objects and their native code live side by side. The WebAssembly spec, for reasons that make good sense, chose to basically make a divide between collectible things and the stuff in the. And so it's been a discussion. We've talked to the people working on the spec and said, this won't be usable for us. And they said, that's unfortunate. What would you need? And we say, this is what we need. And they say, maybe in the next version. It's the normal thing with specs, like people have different desires. What we use for GC in the mono runtime is the mono GC. It does memory scanning and the way, and I can go deep into it, but it's implemented as part of the runtime. It is not built in. It's implemented in part of the WebAssembly that we load, not as part of the runtime that's in the browser. Now, that doesn't mean that we couldn't take advantage of some of the GC stuff that is available in the browser for JavaScript interop and other things. And so we're always looking at extensions to see if there's some way we can leverage them, but we can't leverage it. And a lot of it comes down to basically, like I said, native access to objects and also .NET has some fairly strict rules about finalization ordering and things like that that the WASM specs, at least last time I looked, isn't able to enforce, and that means that it wouldn't be enforcing the rules that we kind of have to enforce.
So we do work with them. We do participate and give feedback on the WebAssembly standardization efforts to try and get as much value out of web platform improvements as we can. In some cases, though, it's just not the right fit for the .NET platform. So we do have to bring our own GC currently. That's still needed. All right. Couldn't the browsers just agree to include many of the features modern, I think this is WASM, what they meant, WASM use, so that we don't need to ship the whole runtime to the browser? In some sense, yes. Like the browsers continue to expand what they support for WebAssembly, and like we saw with SIMD, like as they add things that we can take advantage of in the runtime, we do leverage those features. In some cases, that might mean we can make the runtime potentially smaller at some point in the future. We'll just have to see how the
exception handling is one of those cases where before exception handling existed in the WASM specs, we had to made a lot more code and it was even more complicated. Now there are a couple of iterations actually of exception handling in WebAssembly, and we can take advantage of that. It's still complicated because it doesn't look exactly like .NET exception handling, but we can leverage a combination of the two to do some of the things that .NET has a quite complicated exception handling model that looks a lot like the Windows exception handling model. It's not necessarily an easy lift for browser vendors.
We're trying to rip through these last few questions. Any plans for WebAssembly with WASI in .NET 10? So WASI is the WebAssembly
system
interface, which is basically like a basis for doing like server-side WebAssembly scenarios. And we do have like experimental lab support for doing .NET on WebAssembly using based off of WASI for server-side WebAssembly scenarios. For 10, no plans to ship a stable release of that, or we haven't really honestly been investing much in it. No real roadmap for that work at this time, but we continue to monitor that space to see how it moves. As if server-side WebAssembly becomes an important thing, then we will prioritize it higher. Let us know if you have scenarios where you think it would be.
Yeah, what we're really looking for is scenarios that we can get the value of the work. In 9, we did a lot of experimentation to figure out how close to being able to usable WASI was for the scenarios that we were interested in, and basically we decided that it was getting it to the point we needed for the stuff we needed was probably not the best place to invest our time right now, but we're still pay attention and still are interested. It's just and it's also a community project. People want to work on it. They're open source.
We can participate.
Yeah. It's just the team doesn't have, that's not the focus of our work right now.
Here's a question about, or more of a statement about someone still using Next.js instead of choosing to use Next.js instead of Blazor WebAssembly to have a lighter weight and more performant experience. And that is a valid decision to make. Like compared to, we talked about a bunch of performance improvements for .NET on WebAssembly in this in this session. If you were to really still compare, though, like raw JavaScript runtime performance versus .NET performance when running on the WebAssembly runtime, you will still probably get, in many cases, a good performance boost from just running JavaScript. So we don't expect to win that race. I mean, like we said, JavaScript gets to ship the runtime with the browser. They kind of get the cheat there compared to what we have to do. So if you need top level runtime performance in the browser and you need your app to be absolutely as small as possible and load as quickly as possible, then you might want to look at using a front-end JavaScript framework for that scenario. The benefit of using Blazor is you get to use your C# skills, your C# infrastructure and know-how and libraries. You get the productivity of the Blazor development experience with good enough performance is what I would say. Continuing to get better. So that's kind of the way I think about it. Like the both are valid options and they have different trade-offs. We are definitely optimizing more for productivity, skills reuse, low cost of development with the Blazor development experience. If you really need the fastest runtime, smallest download size, then front-end JavaScript might actually be the right option for you. All right. And then WASM is getting there. Impressive performance improvements. Now we need native GC in WASM. I think we talked about the GC situation. If we can get a GC implementation in WASM that would work for the .NET semantics, then we will, of course, look at using it. Right now, that's not currently an option, but specs change. The web platform continues to improve in various ways, and we are participating in that conversation. And then lastly, someone had a comment about, I think this is about the co-hosting work in Visual Studio 2026, that there are some rough edges. I know when we poked people on social media to try it out, there were definitely issues that people hit. So yeah, if you're trying to do like your day job with co-hosting on, you might hit some rough edges that will make that difficult to do. Totally understand, but please send us those issues. Like as soon as we got that feedback on when those social media posts went out, like the team started, working on bug fixes, getting improvements in for the next preview update of 2026. So thank you everyone who shared the issues that you ran into. Give it a try and hit that send feedback button. Let us know if any issues that you're hit. That will make sure that the experience is as good as possible by the time we ship it come this November. All right. I'm sorry if we didn't get to all your questions. There are a lot of them. We try to get to as many as we can. If you have more, you can also come find us on GitHub or on social media as well. We do hang out there too. Thank you everyone for watching today and participating in the conversation. Larry, thank you for sharing your
it's always a pleasure, Dan.
The great work that you've done in the .NET 10 release. Be sure to give .NET 10 RC1 a try. And with that, thanks everyone for joining. Happy coding. We'll see you next week.
Bye, everybody.
Bye, folks.